Good morning if you're watching this before lunch. This is Mr. Williams, and this is my first attempt at recording a lesson for our astronomy class. And we're actually going to start with the new material for today, which I'm recording this on Wednesday, March 18th. So that's the third digital learning day. And our lesson today, if you've not already looked on eClass, is on neutron stars primarily. So what I'm going to be doing is I'm going to go ahead and try to do the present function. And I'm going to pull up our PowerPoint that is on eClass that's titled DLD March 18th Lesson, Neutron Stars. And I'm going to do slideshow so y'all can see it on full screen. And I'm going to have my little laser pointer here to highlight things as we go. Of course, there's just the title. And again, as you can see, this topic is part of AKS 8C2, which if you want to get a refresher on what the actual AKS say, then go to the actual Unit 3 folder on the content page and look at one of the various PowerPoints we've already seen in class last week and earlier. And again, the beginning of those always have the AKS listed. So anyhow, if you've already worked through the last 2 days, Monday and Tuesday's material, again, Monday was on Type 2 supernovae, building off on what we did last Thursday physically in class, which was Type 1A supernovae and also just regular novae. So we were starting to work through stellar explosions. And again, Monday was Type 2 supernovae. Yesterday got into a lot of different, more exotic stellar explosion types, things like hypernovae, kilonovae, and so on. And now we are focusing today more on the actual end stages that come out of some of these explosions. And again, one of them here, you can see we've got white dwarfs. We've been talking about white dwarfs because that came up in one of our first lessons in this unit on sun-like stars. And again, a white dwarf, at least in this context, is what comes out of a sun-like star when it ejects its outer layers to form a planetary nebula, and the core itself is what converts into a white dwarf. So we're not going to say too much about them in this lesson just because, again, they're older material at this point, but just as a reminder, again, like it says, it can come from a sun-like star, meaning, with a solar mass close to 1, maybe a little bit higher, a little bit lower, or an intermediate mass star, which that's a little bit more massive, somewhere more in the range of possibly 4 to 8 solar masses. But the white dwarf itself, it has a strict limit on its mass, this 1.44 solar masses. Again, that's a special number for us. We introduced that again in the sun-like star lesson. That's the Chandrasekhar limit. Again, if a white dwarf becomes more massive than that, then it starts to run into some problems, and we'll go through some changes, which we're going to get into that here. And again, one other reminder, it says that white dwarfs, again, they don't fuse anything to release energy. They're just releasing residual heat from, having been compressed from a former solar mass core or sun-like star core. But eventually they will dissipate their heat and become what we call a black dwarf, although those don't seem to exist yet. Neutron stars, and again, that's really more the focus for today down here. A neutron star is typically going to be the end stage of a star from somewhere between about 8 to 25 solar masses. And that's the mass of the entire star. Now, however, we can also focus on the mass of the core alone. If the core of a supermassive, or maybe not supermassive, but just a big high mass star is at least 1.4 solar masses, then it could likely become a neutron star. However, it's kind of a narrow range. Again, a neutron star will have to come from something of a core of at least 1.4 solar masses, but anything of about at least 3 or more solar masses, and it will actually totally collapse into a black hole instead. So again, neutron stars really, again, if you want to throw in up here, or just mentally for yourself, 1.4 solar masses to 3 solar masses, that's the very narrow range for a core mass that can actually yield a neutron star. Again, anything larger, and you're looking at getting a black hole as your end stage. All right, so moving along, again, this is where we're still kind of dealing with some of our white dwarf material. I'm going to hide this real quick. But anyway, so the primary difference between these 3 end stages, white dwarfs, neutron stars, black holes, is their density. And again, density, that's something you should have a pretty good idea about from chemistry class, physical science class. But just as a reminder here, it's letting you know that, again, it's a measurement of mass compressed into a three-dimensional space or volume of a particular size. So if you want to calculate density of an object, you would just divide the mass by the volume and you have what you need. Of the three end stages we're discussing, which we have our white dwarfs, neutron stars, and again, this particular image doesn't show a black hole, but that's our third option. White dwarfs have the lowest density of those three. Neutron stars, again, are kind of in between, so they're sort of a medium level of density, at least in this context. Again, they're still way more dense than almost any other thing you can imagine, but they're not as dense as a black hole, because the black holes, we get to say that they have infinite density. And again, that's kind of it's almost a nonsensical statement, but we'll get to that more later on with the material on Thursday and Friday when we talk about black holes specifically. So again, remember that white dwarfs are pretty small for a star. They're about the size of the Earth, sometimes a little bit larger or smaller. And again, their mass range is about 0.4 to about, again, that hard upper limit of 1.4 times that of the sun. Again, that 1.4 solar masses being the Chandrasekhar limit. And so again, think about this. You're trying to take something at least half the mass of the sun, usually more than that, and compressing it down to roughly the size of just our planet. And again, Earth is not even the largest of the planets in the solar system. So that's a lot of mass in a very, very small volume. And you can't try that without some things starting to kind of buckle under the strain of all this pressure. So you get, instead of any sort of normal matter, like normal, again, when we've been talking about stars this spring, and even starting with the sun back in January, we started talking about how, again, stars are a mix of gases and plasmas, where plasmas are broken down into free ions or nuclei and free electrons. And you still have that here with this degenerate matter in a white dwarf, but the difference being that there's basically no room for these different items to move around. Again, we talked earlier on in this lesson, or in this unit, about how this is kind of like trying to cram 20 people into a small elevator. It's not going to be comfortable. There's going to be no wiggle room. For a neutron star, again, we're getting a higher mass range, like we said, about 1.4 to 3 solar masses. So this crosses the Chandrasekhar limit. And again, that comes with some consequences. You have some things change. When we were talking about that white dwarf and how the electrons are crammed against the nuclei, they have some resistance to each other. The electrons do not want to be merged with any protons. And that resistance, we call that electron degeneracy pressure. But the amount of gravitational force acting on a star's core that is over 1.4 solar masses is going to be so powerful that this electron degeneracy pressure just cannot resist it any further. So instead, we do get that merging. The electrons and protons, most of them anyway, not all of them, inside this supermassive, star core is going to, those electrons and protons are going to merge. And this is called inverse beta decay. And as the main product we get is that they merge to become a neutron. One of the videos I was checking out yesterday that's linked to on eClass, it's the one from, so it's Questions with Joe, I believe, the one that he has on strange stars. He kind of describes this as like a subatomic fusion. Instead of nuclear fusion, where you're merging, two different nuclei. Here, we're merging two specific subatomic particles to get a different result. So that's an interesting description, but don't confuse it with actual normal nuclear fusion. But what you get, again, when you have now this core that's mostly made up of neutrons, and they're all crammed incredibly tightly together, and that's what's being shown over here, this middle part of this diagram, we have this neutron-degenerate matter. And we'll talk more about that here in a minute. Again, the inverse beta decay is the active process that makes that happen. So as far as we know, except for one exception we'll get to later in the lesson, neutron stars are about as dense as you can get and have a regular material object. If you try to take something 3 times the mass of the sun and condense it into a collapsing stellar core, then you're going to, again, end up in a situation where there is no natural force, whether it's electron degeneracy pressure, or in the case of a neutron star, neutron degeneracy pressure, that can withstand the crushing force of gravity. So you get the entire mass of a stellar core of at least 3 stellar masses compressed into a point that doesn't take up any space. It's 0 volume, and that's where we can go back to that infinite density idea for a black hole. But again, we'll talk more about that in the coming couple of days. So again, we've kind of covered now everything we need to say about white dwarfs. So going forward, again, today and the next few days, we're focusing strictly on neutron stars and black holes, the more extreme stellar remnants or stellar end stages. And it kind of tells you right here too. One other thing we're going to look at with black holes is Einstein's theory of relativity. But again, that'll be for tomorrow and Friday, not today. All right, so neutron stars themselves, we've introduced them already when we talked about the life cycles of high mass stars, as it mentions up here. And again, this is what happens when, a neutron star is the result of a core of a star, again, about 8 to 25 solar masses, being collapsed so much that, again, that neutron degenerate matter is produced. And again, this is going to take place. This whole process is a byproduct of the type 2 or core collapse supernova explosion. That you don't typically find other methods in nature for being able to turn a star core into a neutron star. And again, we already mentioned this neutron degenerate matter. You see another term here. Sometimes it's used as baryon degenerate matter. Baryon is just a term used for certain types of particles. Neutrons and protons both belong to that group. So that's why that's brought up here. You can see it in the diagram as well. But anyway, so neutron stars are mostly neutrons, not completely, as we'll see. And again, a lot about what we know about their structural composition is still debated. We're learning more now than we have, like in recent years, than we ever have before in previous decades. But obviously, we still don't know everything there is to know about the structure of something so extreme as a neutron star. Now, another couple of terms you see thrown around, especially like, say, if you're looking at a science fiction take on some of this material, is this neutron degenerate matter. Sometimes people just call it neutronium because it sounds kind of like the name of an element with that IUM ending. Some people even call it element 0 because if the periodic table, an atomic number tells you the number of protons in a nucleus. And if you had stuff made out of completely pure neutron material, then it would have no protons, so 0. Hence the name element 0. But again, those are more kind of nicknames than true scientific terms. Neutron degenerate matter is typically the scientific term you see thrown around. So again, one thing that neutron stars have in common with white dwarfs is, again, they don't go through fusion. They don't actively produce and release energy. Instead, again, they just give off residual heat and light. However, they're pretty ineffective or inefficient at transferring heat from their cores to their surfaces, even though it's a relatively short distance. Again, keep in mind, neutron stars are tiny. They are about 20 or so kilometers in overall diameter, not even radius. So that's their entire width across, plus or minus a few kilometers, perhaps. But they, even though it's a small distance, they're not very good at transferring the heat through this very weird material that they're made of. So sometimes, we find measurements of neutron stars that cool off kind of quickly. That's what it says here about cooling off at inconsistent rates. And this link, if you pull this up, if you pull the PowerPoint up and click on this link, it'll take you to an article about that. But again, we don't really know a whole lot of good, solid information about how neutron stars get rid of their excess energy over time, and then therefore what they could turn into once they've run out of their energy. We know that with white dwarfs, they will, theoretically become something like called a black dwarf, where it's just a clump of kind of dead matter, dead stellar matter. But with neutron stars, we don't really have a good model for what they're going to turn into once they've run out of energy. And it's like what it says down here at the bottom. And also, one other thing I'll just point out, this little animation over here, this is actually relatively new data. And this is not just like a little CGI artist's interpretation of what a neutron star looks like. These are actual mapped images, the first of their kind from a neutron star. Now, there's two different ones, not because they're two different neutron stars, but because they had two different teams kind of interpret the data differently. And you can see that the overall image is pretty similar, but there are some differences. And you see those bright white spots and streaks near the South Pole. And presumably those are areas where lots of energy is being emitted, at least at the time of the imaging. And that could have something to do with this star being a pulsar, which we'll get to later in the lesson. All right, so again, we said that the internal structure of a neutron star is kind of up for debate. But like I said, scientists, astronomers, astrophysicists, we've learned more about them in recent years than we have in previous decades. So we have a better idea now than we would have, 5, 10 years ago, obviously earlier. And like it says, the one thing that most astrophysicists agree on is that they're more complicated than just simply being a ball of neutrons. So, previously we've kind of treated them in that simple description, a star made out of neutrons, but there is more to it than that. And we're going to take a look at that here. So first of all, like most stars, including normal stars like the sun, neutron stars are thought to have an atmosphere. However, this atmosphere would be pretty thin. They don't even describe the radius of the atmosphere on this diagram. That first radius down here is for the inner crust, but very, very thin, just because the gravitational pull of this star is tremendous. So any gaseous atmosphere is not going to take up a whole lot of vertical space going off of the surface of the star. And also, it's thought that the atmosphere itself, even though again we're talking about extreme gravity in this around this star, the atmosphere might just be far enough away from the core that it could, in fact, have low pressure that would allow for normal atoms to exist. Just typical atoms, like you would think about from chemistry class. Simple nuclei, though, nothing really complex here, nothing large like silicon or irons, more like, again, of course, hydrogen and helium, maybe some carbon. You see those listed up here. And but other than that, again, the atmosphere's probably not got a whole lot going on with it. Now, what's interesting to me with these neutron stars is they have what we can call a crust, which is a strange thing to say about a star because, again, previously we've only really talked about the fact that stars are, again, gas and plasma in different proportions, which, again, you can't walk on either of those things, even when they're under high pressure. But don't forget, a neutron star is coming from the core of a star, previously a supergiant star or something like that, and that core would have previously been plasma. But here, with this intense pressure, we can go from a very thin gaseous atmosphere to an outer and inner crust they behave kind of like solid material. And you can look more into this sort of thing. There's actually something you can read about called star quakes with neutron stars, where it talks about cracks in this crust and how that can release some large amounts of energy, kind of like how earthquakes do here on Earth, but obviously a pretty different situation for a neutron star. But anyhow, it says the surfaces of these stars are thought to be somewhat like a solid, and it may contain the same elements as the atmosphere, but broken down, no longer normal atoms, into a mix of nuclei and free electrons. So in other words, this outer crust would be structured basically like a plasma, again, nuclei and free electrons, but compressed to the point where, again, it's behaving more like a solid. So it's a very strange thing. Now, below that, we can have this inner crust, which, again, is still not going to be very thick either. Again, like it says here, maybe half a kilometer. That's it. You can walk that in minutes, that distance. But anyway, it says it can be composed of heavier nuclei, possibly. These are nuclei that might have survived photodisintegration during the Type II supernova that could have produced this star. And this layer may also be more rigidly structured. With the nuclei, some of them may be forming like a crystal lattice, like you might see, with silicon dioxide molecules making up a quartz crystal lattice, like in an actual normal solid. But even if that is the case with these nuclei, there's going to be still a lot of free electrons moving around, but also now a lot of free neutrons. So this is where the neutron star actually starts to take on more of that neutron identity. And in fact, not only are the neutrons moving around, they may be in a really hot superfluid state, which here on Earth, we can make superfluids, but they have to be incredibly cold. In this environment, though, that can be kind of achieved in the opposite way. And a superfluid basically means that it's like a liquid, but with virtually no friction. So you have very little energy loss as the particles move around. And that'll actually become more important in a little bit when we talk about the magnetic fields of the stars and that sort of thing. The outer core. So again, now we talk about the core of a neutron star, which the whole star used to be a core. So we get cores within cores, as it will. It says there are no nuclei at this point in the outer core, only free electrons, neutrons, and protons. So now you've only got individual subatomic particles, no more complicated structures than that. And here we've got protons. Again, they're free at this point, like I said, and they're moving around. And again, in a superfluid state, that means they're moving around at a pretty high rate of speed, and that means they can act as superconductors because they are charged particles. Protons being a positively charged particle, and we'll come back to that. All right, in the inner core, this is, again, literally, you can see in the diagrams the question marks here. So again, this is the most conjectural part of the structure of a neutron star. And that's because we have a lot of options for what may be there, and it could be a combination of different options. And I'll go ahead and just flip to the next screen because it nicely diagrams these out. So it says here, we got this traditional model of a neutron star, which says, okay, well, in the inner core, you've got tightly packed nucleons, which nucleons, again, is just another kind of a group name, if you will, for protons and neutrons, because they're normally both found in a nucleus. But it says tightly packed nucleons with their quarks intact. So in other words, this traditional model says that the core contains protons and neutrons, and they're really dense. They're very close together, but otherwise nothing especially strange going on about them. But now at the bottom here, we've got a few other models that could be describing what we have instead, or perhaps in addition to these normal but hyperdense protons and neutrons. So one possibility, they call it a quark core, and that's because quarks are the smaller particles that make up protons and neutrons. And this model suggests that the protons and neutrons have such great pressure on them that they're no longer going to act as single collections of quarks. The quarks that make them up will be broken free. And the two kinds that are found in protons and neutrons are up quarks and down quarks. Those are their names. So this model suggests that the core of a neutron star is basically just free up and down quarks. Now, a slightly revised model says, okay, that might be true, but some of those up and down quarks might actually help form a third kind of quark, which is normally not seen in typical matter, called a strange quark. And that's literally its name. That's not just a description. That is the name of the particle. Like how we call a proton, this little particle is called a strange quark. And if that's the case, then it could be that these strange quarks then rejoin with some other quarks. And if they do that in certain combinations, they can make a special kind of particle called a hyperon, which is a terrific name. It sounds like a great science fiction term. But that's a possibility. These hyperons that include strange quarks might be making up the core. And then one other model here that I don't really get into anywhere else in the lesson is that we might, instead of getting hyperons, which you can see each have 3 quarks apiece, we might instead get some particles of just 2 quarks. And one of them would be a strange quark. The other one would either be an up or a down. And these are called kaons or kaons. And if we have a bunch of these kaons, then it can be called a kaon condensate. So anyway, these are some different options for what might be found in the core of a neutron star. And again, it could be that none of these are wrong and maybe all of them are correct in different proportions. Or maybe it is just one of them is right. We don't know. And that's the people are astronomers and astrophysicists are trying to learn as much as they can about this stuff. But it's kind of hard to, given the extreme nature of these stars, and many of them are far away, hard to study. But we've been able to learn more about them than ever before in recent years, like I've said. All right, now moving on to some of the other properties of neutron stars. It says all neutron stars have incredibly strong magnetic fields, typically billions or more, actually, times as powerful as Earth's. Astronomers do not have a full understanding of why this is, but there's at least 2 main factors at work here. One, again, and this goes back to our superconducting protons in the outer core, at least. These charged particles, again, these protons, and electrons might play a role here as well, are moving, again, at very extreme velocities. And that, again, that means that they're going to be able to help produce a magnetic field. That's actually something, the movement of charged particles to produce a magnetic field is something that Michael Faraday, an English scientist, discovered back in 1820. That's something we've actually covered recently in our physics class. And so if Michael Faraday can figure out that just electrons moving at pretty typical speeds in a wire can produce magnetic fields that are noticeable, then surely protons zooming around within the layers of a very strange environment like the interior of a neutron star, they can produce tremendous magnetic fields that don't really have any equal anywhere else in the natural world. Nothing has a magnetic field comparable to that of a neutron star, except even stronger magnetic neutron stars, which we'll talk about those here pretty soon. So again, incredibly fast charges can generate incredibly powerful magnetic fields. That's the key idea to this factor. The other factor is a conservation idea. I mean, we've talked about conservation of things before, especially conservation of angular momentum. That's been a big deal a few different times throughout the course of the semester. And but here, we're not talking about conservation of angular momentum, but instead the magnetic field of a star. What seems to be the case is that a neutron star, even though it's much, 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 much smaller than its progenitor star, like a supergiant that it may have come from, it seems to conserve the magnetic field that supergiant star had. But the interesting thing is that if you try to apply that same magnetic field from a supergiant star across the incredibly tiny surface area of a neutron star, then that actually tremendously amplifies the strength of that magnetic field. Keeping the magnetic field flux the same across a smaller radius will make the field stronger. And that's what we're seeing in an extreme way here. So this is probably an important factor. Different factor here, or a different property of neutron stars. They spin around really, really fast. And so just as how neutron stars conserve their magnetic fields of their progenitor star and amplify it across a small surface area, they basically do the same thing, again, with their angular momentum to gain incredibly fast rotation. Just like how there aren't really any natural objects that can compare to the magnetic field of a neutron star, same thing with the rotation of a neutron star. Nothing really rotates faster than a spinning neutron star. So stars always rotate. The sun's rotating right now. Other stars that you can look at in the night sky, they're rotating as we speak. And even when a star starts to go through a type 2 supernova, like a supergiant star would do, it's still spinning in the midst of all that explosion process that's going on. And so as a star, and specifically the core, because that's what's going to turn into the neutron stars, especially, collapses into the roughly, again, 20-kilometer radius that will become the neutron star, its rotational velocity and momentum is going to increase since the size of the object is decreased. And again, we've talked about this in the past, this conservation of angular momentum. One example is, for example, the conversion of a stellar nebula into a protostar. Protostars spin faster than the stellar nebula that form them because they get smaller. Gravity is condensing or compressing them. Again, a very common example, almost always given when talking about this process, conservation of angular momentum, is like an ice skater. If an ice skater is spinning around with their arms out and then all they do is just pull their arms into their chest, then they will start spinning faster for no other reason. They're not kicking their feet to try and spin themselves up. It's just going to happen because their angular radius is reducing. And since velocity is going to depend partly on that radius, the angular velocity and the angular momentum has to be conserved, and so the velocity will increase. And again, you can actually try this yourself. I know you're at home all this week. I don't know if you have like a little spinny chair or an office chair at home that you're working with on a computer or whatnot. But if you do, spin yourself around in the chair with your arms out, and try to spin pretty quickly. But then pull your arms in, like I said, to your chest or so, and you will speed up. Just as a process of conserving your angular momentum. It's a pretty neat effect. So give it a try if you can. Neutron stars spin so rapidly, like we said, nothing really compares to this, that their rotational period is usually less than 1 second, or so a fraction of a second, maybe 0.2 seconds, 0.8 seconds, so something in that range. However, again, it can get much faster than this. That's just more of the typical rotational velocity. Neutron stars in binary systems that can draw mass from their larger partners can often get their spin accelerated by the infalling matter. That's what's being shown in this diagram. to the point where their rotational period can actually be in the thousandths of a second. So they can rotate completely. And this is small for a star. Again, we're only talking about, maybe again, a roughly 20-kilometer radius here, or a diameter. But the whole thing, imagine rotating a giant city in 1,000th of a second. That's kind of what we're talking about. And again, these are called millisecond pulsars, and that's going to lead us into pulsars in general. So, and you've probably heard this term before. It's a fairly common term that pops up from astronomy jargon. But if you're not familiar with what it is, it's a neutron star that rapidly rotates and seems to, from our perspective, emit pulses of energy. So if you're looking at it with a telescope, especially, a powerful telescope, maybe a specialized one like an X-ray telescope or radio telescope, you will then see at its location in the night sky, again, it'll appear to get larger and brighter, and then dim and smaller, and then back and forth. It'll keep appearing to pulse. And that's why they were given the name pulsars. We observed them before we really knew what they were. And this was first detected, by the way, in the 60s. That's kind of where this dates back to. The 1960s is when we first really found this, and it was found with a radio telescope specifically. But we've discovered many, many more since then. And one thing that's kind of going on to make this pulsation effect happen is that, kind of like with Earth, how our rotational axis and our magnetic axis are not, directly in line with each other. They're misaligned. And that's why magnetic north and geographic north are not the same place in the North Pole or in the Arctic Circle. The same thing is going on for a neutron star. Most of them are not going to have a strict alignment between their magnetic axis and their rotational axis. So as they spin on their rotational axis, their magnetic north pole is going to keep pointing in different directions. And the same thing with their magnetic south pole. Now, what's interesting about these pulsars is that they're so energetic and their magnetic fields are so powerful that they actually end up accelerating electromagnetic energy away from their north and south magnetic poles. And this ends up taking on the form of energy beams. And it's a wide range of energy. It's not just one kind. You've got radio, X-ray, gamma. Those are at least the main three you detect, but others, just plain old light can be shot out of these beams as well. And since we have this misalignment from these poles, the rotational axis and the magnetic axis, the beams itself can be swept around. They're not locked in place like the rotational axis is. And so you get this beam of energy sweeping around in the universe, pointing in lots of different directions, and again, these rotations happen quickly. We're talking about, again, fractions of a second. So you have what is basically like the most extreme version of a lighthouse. You've got a spinning source of electromagnetic energy sweeping its beams around and around and around. And in fact, we call this model of pulsars the lighthouse model. It's just it's too convenient of an analogy not to use. And kind of like how we talked about, if you looked at yesterday's lesson on exotic stellar explosions, if you read about gamma ray bursts, GRBs, they emit beams in our direction sometimes. Same thing with pulsars. We can only actually find a pulsar if its beams are pointed in such a way that they will sweep across Earth as the star rotates. So if that doesn't happen, we won't know that neutron star is a pulsar. We might detect the neutron star, but we won't be able to see those beams because they're not coming toward us. What else do we have here? It says, in fact, pulsars, they do not pulsate in actuality. So in other words, this is not like an actual pulsating variable star, like a Cepheid variable or an RR Lyrae variable, like we talked about in Unit 2. They don't actually get bigger and smaller in terms of pulsation. Instead, the beams that point to us every so often seem to make them pulsate because they get brighter and dimmer and brighter and dimmer. Also, one other thing to know here is that it's very likely that most neutron stars are pulsars, because the two main factors at work here, again, are the very powerful magnetic field and the rapid rotation. And all neutron stars have those properties. So most neutron stars, even if we can't tell directly that they're pulsars, they probably are. And here's a nice little diagram you can take a look at. It's from a radio observatory organization that's put it together. And you can take a closer look in the actual PowerPoint if you want. But it's got a nice diagram showing the rotational and magnetic axes and how they're misaligned. Now, so we said most neutron stars are probably pulsars, but maybe not all of them. This is probably the major exception, and we call these magnetars. And these are neutron stars that have the most ridiculously powerful magnetic fields that we know of for any type of normal object. Maybe some black holes have a more powerful magnetic field, but otherwise, this is kind of it. So as a typical neutron star has a field of about 1 trillion Gauss in strength. And again, Gauss is a unit of magnetic strength, kind of like we've mentioned Teslas and nanoteslas before. Gauss is another unit that can measure the same thing. Again, a normal neutron star, its field is about 1 trillion Gauss in strength. Earth's is about 1 Gauss, excuse me. So again, just no comparison. But a magnetar can be about 1,000 times more powerful. Again, it can be measured in 1,000 trillion Gauss for its magnetic field strength. And again, if you were to get within even hundreds of thousands of miles of this star, maybe you're traveling along in a spaceship or something. If you have your space credit card on you, it's going to be completely wiped. And so is everything else on your spaceship. Of course, it depends on electromagnetic systems. It's going to be shut down as well. Get any closer, and this can be lethal. The magnetic forces could tear apart your atoms into kind of just like a mist of particles. So these are actually pretty dangerous items if you get close enough. Of course, that's not really in danger for us. None of these are really nearby to Earth or our solar system, which is a good thing. Again, we don't really know why magnetars are so powerful magnetically. And again, it mentions here that they're less common than pulsars, and the two are not the same. A neutron star is not going to be both a pulsar and a magnetar. But some astronomers think that it may have to do with their age. It could be that magnetars are just very young neutron stars, meaning they've just recently formed out of a type 2 supernova. And it's been supposed or proposed that they may kind of calm down, magnetically speaking, in a range of about 100,000 years, which is pretty short for astronomical timescales. So they may go back to a normal magnetic field strength of a neutron star, and they may actually even convert into a pulsar at that point, because they might actually be able to increase their rotation rate if they weaken their magnetic field. All right, moving into the tail end of the lesson here, we got quark stars or strange stars, and these are kind of an add-on this is another possible stellar end stage. And so when I say possible, this is theoretical. No one's found definitively a quark or a strange star yet, although there are candidates. There are some neutron stars and also some supernova remnants that house energy sources that might actually be some of these guys. And so, again, one possible outcome of the extreme gravitational forces acting on the core of a supermassive star is that it may become something kind of between a neutron star and a black hole. And by between, I mean in terms of mass range. So, again, this might occupy a very narrow mass range around 3 solar masses. If the core of a star is about 3 solar masses, maybe it turns into this instead of a black hole. Another possibility, too, is that a neutron star might find itself in an opportunity to change into a quark or a strange star, maybe by gaining mass from a binary partner through mass transfer. But anyhow, they're called quark stars or strange stars, these ideas, these theories. And they're called that because quarks, again, are the fundamental particles that make up hadrons. And by fundamental, we mean they can't be broken down into anything smaller, at least that we've been able to find so far. And that's been true of quarks. We've known about this, for almost half a century now, maybe longer. But they are hadrons are composite particles like protons and neutrons. Hadrons are actually a larger category than the baryons we mentioned earlier. So things like protons and neutrons include quarks. Electrons don't. They're actually a totally different class of particle called leptons, and they're kind of like quarks in that they can't be broken down further. Quarks in any sort of normal material are never going to be found alone. They're always what we call confined within a hadron, either with 2 other buddy quarks, maybe just 1 other buddy quark. So usually in 3s or 2s, although there are some exceptions to that. And what keeps them confined together is the strong nuclear force. We've talked about that before. But the strong nuclear force has a force particle that it acts through, kind of like how electromagnetic force acts through photons. The strong nuclear force acts through gluons, and that's actually, yes, what they're called, because they help kind of keep these particles glued together. And there's 6 total different kinds or flavors of quarks. The most normal ones are up and down quarks. Those are the ones that make up protons and neutrons. And then you also have 4 others, and they are not found in normal nature because, kind of like how certain nuclei are radioactively unstable, these guys are kind of like that. They don't stay in their normal form for long. They then change into something else through decay that involves the weak nuclear force, which we haven't really talked much about. But a top and a bottom quark, they will easily decay. Charm and strange quark, they will also easily decay. And strange quarks are going to be the important ones here because they can actually potentially be formed when you have a bunch of deconfined up and down quarks moving around together. If there's enough pressure to kind of fuse an up and a down quark, they can actually convert back into kind of an anti-decay into a strange quark. Almost like how protons and electrons can go through inverse beta decay to form a neutron. It's a very similar kind of process. And if you, again, we talked about hyperons a little bit earlier. A hyperon is something that you could make, a particle you could make using strange quarks and up quarks and down quarks. And these things might help make up these possible quark or strange stars. Now, a little bit more here about them, about these stars, these theoretical stars. So, and another thing that also is possible here is that this kind of quark matter, where it's not confined to particles like protons and neutrons, it might not only be found in a quark star or a strange star. It might also be, again, in the center of the core of Neutron Star. We discussed that earlier. But anyway, it says either in the inner core of a neutron star or perhaps in the main mass of a strange or a quark star, the quarks, again, are deconfined. They're no longer contained within a hadron like a proton or a neutron. Now, another term you may have heard of before, especially if you've ever looked into any of this stuff, it says this mix of quarks and gluons can be called a quark-gluon plasma, or quagma. That's a real scientific term. Sounds kind of funny, but that's what it is. And this quagma, like we said, it can fuse. Again, if you can get some of the up and down quarks to sort of fuse together, they can possibly form into a strange quark. And then you've now got enough strange quarks that this can be called strange matter. And it actually might be some of the most stable material that we could think of. And again, if it were to be released in a kilonova, where, say, maybe 2 neutron stars collide and explode, if they include some of this strange matter, or maybe quark stars, again, themselves exploding, then this strange matter might get out into the universe at large and might actually be able to, it's so stable, it might be able to convert normal matter into more strange matter. And this video kind of gets into that. And so we actually have 2 videos on E-Class today that kind of get into that possibility, which is kind of a weird thing. All right. Again, I mentioned on the last slide that neutron stars might be able to change into quark or strange stars instead of just, a quark or a strange star forming directly from a supernova. And if that were to happen, it would actually in itself produce another really powerful explosion. This could be called a quark nova. And it's so powerful that it might be a sort of a third cause for gamma ray bursts. So, yesterday's lesson mentions hypernovae and kilonovae being possible causes for GRBs. This might actually be another one. But that is the end of this lesson. And I'm going to stop recording. All right, see you later.